Y'all remember Excitebike, right? It's not just me. That old racing game on the NES, where you're going up them ramps, and jumping, and landing, and if you're anything like me, you're bouncing, not realizing why you can't finish the course by the cutoff time. Well, this bothered me for a very long time. I think until I got to university, when someone pointed out to me the real way to play Excitebike is to adjust the angle of your bike. See, when you hit a ramp, the ramp bestows upon your exciting bike a certain angle, right? You go into the air, you're diagonal, you're in the sky at an angle. And if you just land on the ground that way, your bike's gonna bounce and you lose speed. And since this is essentially a racing game, you don't want to lose speed. Now, the way you get around this is just by tweaking your angle in the air. You want to hit the ground flat, or if you're going to hit the ramp, you want to hit the ramp at the same angle, right? So you just want to be parallel to the surface that you impact with. So Excitebike becomes this game of like these tiny, minute adjustments of your bike's angle. It's beautiful. There are other elements to the game, of course. There's like obstacles on the course, there's other AI controlled racers, but for this slice, what I'm really interested in is replicating the ramps and the jumps and that bike angle, and I want to see how far we can take it. So we're going to use the fantasy console, Pico-8, to make our own little prototype of those jumps and bounces and little angle adjustments. Let me give you a little table of contents at the top here in case you want to follow along, or if you're, implementing and you want to just jump to a specific point of the video. Here's what we're going to do. The first thing we need to get working is just basic motion, just straight ahead. We want this to feel decent, and we want the stopping to feel decent as well. We're not going to do any brakes. We're just going to let friction slow us down. Then we got to figure out how to draw the ramps and how to make the player move up and down those ramps. A little bit harder than it probably seems at first listen. And once the player can kind of just go smoothly up and down the ramps, how do we make them jump, right? How do we give that player some sort of Y velocity to make them go up? And once they're up there, how do we simulate something like air resistance and gravity? And then finally, the real meat and potatoes, or the real tempeh and taters, if you're one of my plant-based buddies. How do we handle the angle of the player? So how do ramps change the angle? How does the player align themselves to the ground? What causes bounces? What causes crashes? All that stuff. So by the end of this, we're going to have a very basic but very much functional proto Excitebike. So let's roll. Well, before we do anything, we need some sort of visuals, right? I never promise you much, but I did put together this little person-shaped creature on what I guess is a snowboard of some kind, and I raised the back of it a little bit so it's got, like a little, you can imagine a thruster here. And to prepare for the eventual angle stuff, I made little angle versions of the guy. There you go, check it out. We're going to be spending some time with this fella and just get to know him a little bit. So anyway, let's think about this little plank of polyethylene, or whatever it is that snowboards are made of these days. We want to accelerate when we press a button, and then we want to decelerate when we let go because of friction with the ground. It's just like the real world, except there's a lot more Lua in this world. So in order to make this happen, we need to think about what our player object looks like and what kind of properties that player object has. So we start off with what is probably the obvious bit, which is X and Y coordinates. And we're going to initialize the player at X equals 16, Y equals 64. And for now, Y is going to be constant, right? We're not moving up and down. We're just going to be moving left and right. dx is our velocity, and ddx is our acceleration. Shout out to all my math nerds out there. I hope that notation is satisfactory for y'all. Dx velocity, ddx acceleration. So every frame, what we're going to do is check to see if the accelerator button is held. If it is, we'll first add acceleration to the velocity, right? The player is getting faster, but we're also going to use this min function here to add a limit. So if we just constantly add our acceleration to our velocity, we are going to reach ridiculous speeds very, very quickly. So we need to cap it. And so what I have here is I've defined this constant player max dx. I've set it to 3 for whatever that's worth. And so the player will accelerate until it reaches a velocity of 3, at which point it will stop. It will stop getting faster. I mean, not stop completely. You know what I mean. If the button isn't being held down, we want the player to slow down, right? The in-world reason for this is because of the friction that the player is experiencing with the ground. We can represent this as a gradual decrease in dx, our velocity, until we reach some really small value, at which point we'll just clip the velocity down to 0 to make it look more natural. If we don't do that, it just takes a really long time for the player to reach 0 velocity, and it looks kind of weird, like there's almost like almost not frictionless, but a very slippery surface, which is a little bit not what we want. So yeah, I've defined another constant here, friction, and we just multiply the dx by that constant each frame until we reach a small value. So we've already updated our velocity, but we also need to update the x position by that velocity, otherwise the player is not gonna move anywhere. Okay, so here's what our course looks like. You can, again, use your imagination. That blue straight line is the road, and those blue circular-ish things are just, think of them like rocks. So I needed to have some sort of scenery so that when the screen is scrolling by, you can see something moving, right? The straight line doesn't show off any motion, any sense of motion. And then on the bottom of the screen, you can see I've printed the controls, so that when I'm pressing controls, you will know what I am doing. And also the player's x position and velocity. Right there. So x is currently 0, dx is also 0. And if we accelerate, we'll see the player start to move. There we go. And you can see the dx gets to 3 and stops, so we know our cap is working. You probably also noticed that I added some particle effects to the back of the player's board just to make this a little bit more exciting to look at. Now, when I've been holding down the accelerator here. When I release the accelerator, we should see the velocity gradually decrease to simulate friction until the player comes to a stop. And there we go. And that feels pretty good. He stops at about the amount of time that I want him to stop, and he reaches the top speed at about the amount of time that I want him to reach top speed. So this, I think, overall feels pretty good. So we can call the basic linear motion part done. So let's look at ramps. If we look at Excitebike, we can see that the courses are really just straight lines combined with the occasional sort of triangle wave type line segments that are the ramps. And somewhere in the deep recesses of my brain, this reminded me of linear functions from old math classes. That's what I decided to go with for drawing our course. So what we're going to do is start off by drawing a line of y equals some base value, which I've chosen to be 72 here. And that's the baseline of the course. That's that straight blue line we were working with before. And we're going to extend that line on either side of the player by some number of pixels. Here we're going to start 64 pixels to the left of the player and continue to draw that line until we're 112 pixels to the right of the player. That ensures that the line extends all the way across the screen with a little bit of extra for good measure. We're using Pico-8's pset function here, which means that we're setting 1 pixel at a time. We're just turning that pixel blue one at a time, rather than using a line function to just draw a line like a normal person would do. But trust me, this will make things easier when we start to draw the diagonals. Now for the ramps. Recall again our old math classes when we had equations for lines. So usually they're presented in a way like y equals some linear equation that depends on x. For example, y equals 2x. So you know what x is, right? In the y equal 2x case, if x is 3 as we travel in the x direction, then y is going to be 6. So we know what x is, and we just need to calculate y. Since effectively what we're trying to do here is just tell Pico-8, for every pixel moving in the x direction, y is either going to be 72 or it's some other value that you can calculate by taking the x value. So our course, or our level, is just a series of those y equals some calculation based on x functions. And now that we know how to think about a level, we can put that into code. And I've defined this level table here to hold information about the level. And the first thing we know we need to have in the level are these ranges, these ramps. I've defined x start and x end values for the first and last x positions that we want the ramp to be drawn at. And this is the interesting part. We define a function, a function f that will do the calculation for us. So you can ignore the first argument here, r. This is just referring to the current range. It's like a programming language weirdness. So when we see inside this function that we're saying r.x start, that means this range's x start value, which would be 80 in this case. For this function, we're taking our y base value, which we know from earlier is going to be 72, and we subtract the difference between the current x position that we're drawing and the starting x of this range. And I should point out that in Pico-8's coordinate system, moving upwards means y gets smaller. So if we work out the math on this little y base minus x current minus r.x start, what we end up with is a line that's going diagonally upwards from left to right. So just having the ranges doesn't get us very far. We actually need to look for them. We need to tell Pico-8 to do something with that data. So what we can do before, we had that loop where we were drawing from minus 64 to plus 112. We're going to add in this find range function call. I'm not going to put the implementation here, but you can check it out on GitHub. And what this is doing is just checking that list of ranges that we were just looking at to see if at our current position, is there a range here? Do I draw at 72 or do I need to do some calculation? And if we find that we have a range, if a range exists, then we don't draw at 72. We instead update the y value to some other value and we set the pixel there. So let's have a look at how this actually looks on the screen. So we'll reload and hey, there you go. So we've got a line going diagonally upwards from left to right, but it only goes up. There is no down part. And again, that was because we just said from 80 to 96, draw a line from left to right going upwards. We did not do the going downward part. That's a different equation, right? If you remember your math class, you need a different function to do that calculation. So let's add that in so we can have a real ramp and not just this one. No big surprises here. What we're going to do is from 96 to 112, we'll just have, we inverted the calculation a little bit. So rather than subtracting x start from x current, we're going to subtract x current from x end, the end of the range. And if we do that and reload, we got a ramp. There you go, both sides. Perfect. That is exactly what I want to see. What's kind of cool and interesting about this way of drawing the course is because we know we're just working with some really common linear equations, we can very easily change the height of the ramps by just tweaking a few of the parameters. So for example, if I wanted to have a ramp that was steeper than the one we just drew, I can just multiply part of our equation by 2 on both sides. And instead of the kind of normally looking ramp that we had in the last version, let's reload. There we go. We get a much steeper ramp. It kind of draws kind of funky, but whatever. We're not going to worry about that for right now. And similarly, if we multiplied it by a number smaller than 1, we would have a much more shallow ramp. So we can actually control the shape of our course pretty easily with this approach. Now, we have not solved all our problems yet because what's going to happen is when I approach this ramp and try to go up it, we just go right the heck through, just blowing right by the interesting part of the course. So we did not add the code to tell the player to do the Y motion. We only told Pico-8 to draw it, right? We need to tie these two things together. My initial thought when I was trying to figure out how to make the player move up and down the ramp was to give them a Y velocity, right? Currently they have an X velocity. They move in the X direction. It should be this way. And so if we want them to move this way or this way, you know, reasonably, we would want to give them a y velocity. I think the correct way, by which I mean the mathy way to do that, is to take our x velocity that we already have and split it into x and y components. And in order to figure out how to do that, I'd have to figure out what the slope of the ramp was. So like steeper ramps would have different results than more shallow ramps, and all this started to feel a little bit messy because we don't actually know the slope of the ramp, right? We'd have to calculate that and then use that to in turn calculate the y velocity, the y component of the velocity. This felt like way too much work for what I was trying to do. I was like, this is too much math. There's no way they did it this way on the Famicom. Maybe they did, but I doubt it. It occurred to me though that I already know exactly the line that I want the player to follow. I want them to follow exactly these y values, maybe with some offset to account for like the size of the sprite, right? But I know exactly the y values. There's no need for me to calculate it or give them any sort of velocity. I can just force the player to exactly the y value that I want them. And as far as the player is concerned, they're not traveling in the y direction. They don't know about that. They don't need to care about that. So let's write a couple lines of code that will use exactly the y coordinates that we get back from when we look up our ramp x and y coordinates, and we'll just force the player to that y value using the same function. So we're gonna assume a y value of 64 for the player. So you may remember we chose a semi-arbitrary value of 72 for the ground. 72. The player is 8 pixels high, and so we want the player's x coordinate, or I'm sorry, y coordinate, which is going to be right here, to be 64, right? 72 minus 8, based on the coordinate system being inverted, gives a player's default y value of 64. So we start the player at y of 64, and we check for a range based on the player's current x value. If we find one, if range is not nil, then we overwrite the player's y value to the y value of that ramp. And then we pass that y value into a player update function. And that's where we'll kind of do that 8 pixel offset, right? We'll do the sort of dark magic over there. But that's all we have to do. We can take a look at how that looks. As you can see, I'm printing out both the x and the y value, the coordinate values on the screen now. And as we advance towards this ramp, you'll notice that the player's y value changes slowly as we proceed over the ramp. We can do the same thing here. We go back to 64 right when we get to the ground. And as we proceed up the steeper ramp, we'll notice that the y value changes more drastically as we move. Now, there is one small problem, and it becomes evident when I was just moving very slowly over the ramp. Let me go full speed over the ramp and you'll see what happens. Wham! So our cheat of not splitting the velocity into x and y components results in very unrealistic travel over these ramps, right? So he's able to cover an enormous amount of y space because we're not breaking the velocity down. So we have to have some sort of cheat to slow the player down based on how steep the ramp is. Now, in the real world, if you're going to be, I mean, there's not a two-dimensional real world, but let's say there was. If in the real fake two-dimensional world, if you're going to be traveling up a ramp like this, your velocity would be spread out across the x and y directions. So you'd be covering the same total distance if we account for both x and y. But here we're not doing that, right? We're just continuing to update the x distance traveled at the same rate, regardless of whether we're on flat ground or on the ramp. So as a result, our guy is getting all that y distance for free, right? He's covering a lot more ground than he should be. So again, the real way to solve this problem looks like a bit of math where we break the velocity down into these two components, but we're not interested in doing a simulation here. We're interested in getting this thing working. So we can cheat a little bit. We're going to start by adding a component to our ramps that indicates some degree of steepness, right? Because we do want the player's x velocity to change depending on whether the ramp is this kind of normal ramp or this big old steep ramp, right? These are going to have slightly different behaviors or slightly different effects on the player's gravity. So In our range structure, when we have a function that tells the player which Y position to move to and which Y position to draw the ramp at, we'll also return an additional integer. And this component will indicate how steep the ramp is. And we'll say that negative numbers indicate some sort of upward slope, and a positive number indicates some sort of downward slope. You can think of it like this. Here's a normal ramp, and we'll say that the slope on this side is going to be -2, and the slope on this side would be +2. We might also want to have a really steep ramp that looks like this, and we'll say the slope on this side is -3, and the slope on this side is +3. And then if we wanted to have a nice little shallow ramp, like a little bump, we'll call this -1 and +1, right? So that's how we'll sort of indicate, looks like a sad face. That's how we'll sort of indicate the slope of our ramps. But when we call our range function, we know we're going to get back an angle that indicates the slope or the steepness, and we'll also pass that into the player's update function. And we'll use that to modify the rate at which the player moves in the x direction by some multiplier of the absolute value of that angle, right? So really, it doesn't matter to us at this point if the slope is -2 or +2, or if it's -3 or +3, right? The sign doesn't matter. What matters is how steep it is. And so we'll multiply the player's dx by that factor. And we can actually change these values around to come up with one that looks and feels good depending on those ramps. Here for shallow slopes of 1, we'll have the player moving at 90% of their actual speed in the x direction. For normal slopes of 2, we'll have them move at 80% of the x speed in that direction, the x velocity. And then for super steep slopes, we'll reduce them to only 70% of their actual speeds. And these are just initial values. We will probably need to tweak them later as we add more functionality, just to keep it feeling nice. So let's take a look at how that changes things. So you can see it's still pretty snappy, but there's a definite slowdown when the player is going over the ramp. It does feel more like the ramp is impacting the player's x velocity. Astute viewers may have noticed that the dx value that's being printed to the screen itself doesn't change, and that's because, as we saw in the code block, we're not actually changing the dx itself. We're modifying how much of the dx is contributing to the player's new x position. I think the change is a lot more noticeable on the steeper ramp. You can see here it feels like that ramp is really impacting the player's speed when we travel over it. It feels heavier, which is good. We want that feeling. Okay, this does look a little bit goofy though, because there's no jumping going on, right? Like it's just, this player is going over a ramp at full speed and getting 0 airtime. So that's the next thing we have to address, I think. At this point, we probably do have to start thinking about how to give the player some sort of Y velocity. We're not going to cheat anymore. So when they reach the top of the ramp, what we want is for the player to all of a sudden have a whole bunch of Y velocity, and that should launch them into the air. So no cheating. The timing of this Y velocity kind of depends on the shape of the level, right? It depends on where the ramps are. So whenever there's a ramp, like the peak of a ramp, we want some sort of Y velocity to be added to the player that will launch them into the air, creating a sweet jump. We can go back to our level structure, and below where we have our ranges, we'll also add a entry in the table for jumps, and we'll position the jumps to be right where the peaks of the ramps are. So you can see here, we'll give it an X position. That's when the player reaches that position, it'll fire that jump. And we'll include a dy, and this is the value that we're going to assign to the player's dy. So this is what's going to be added to the player's y velocity that will cause them to fly gracefully into the air. I'm also including this used flag here to indicate that the player has already passed over that booster and it's going to be not used anymore. Otherwise, there's a possibility that it could be detected and used multiple times, and that would cause the player to go really high into the air, and we don't want that to happen. You can think of this less like the player jumping, and from a data standpoint, it's more like running over a boost tile in Mario Kart or F-Zero or something, it's just kind of like giving the player a little bit of extra velocity as they pass over it. So it's gonna look like the player is jumping because they're going over a ramp. But actually what's going on in our code is we're just kind of injecting a bunch of Y velocity to the player at certain points on the course. Anyway, so for our first ramp, because the peak of our ramp is at 96, x equals 96, that's where we're going to put our jump. What we would expect to see here is when the player reaches the peak of this ramp, they attain some Y velocity and they fly gracefully into the air. But we actually haven't completed the implementation of, let's say, motion in the Y direction yet. So when we do this, here's what's going to happen. Whee! So we have definitely given the player a Y velocity, but we forgot to implement gravity. So while we're not aiming for a simulation here, gravity is one of those things that we do probably want to implement and account for. So let's go back to our code real quick and figure out how we can do that. Let's look at how gravity can kind of be represented in our little world here. Here's our ramp. And let's say we've got our player, and let's say he's just gonna run over the ramp. So he's just gonna fly into the air like this. And we're giving him some Y velocity of minus 4.5 because recall that in Pico-8's coordinate system, minus velocity means you go upwards. And right now what's going on is we just keep minus 4.5. So at every frame, the player just goes up, 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 because we're adding minus 4.5 to the player's X position each time. What we actually want to happen is for the player to have some initial velocity of minus 4.5. They go up that far the first frame. And then gradually they start to go up less and less until they plateau, and then they go back down. So what we can do is set some constant value, because again, that's how gravity works. We'll set it to a ddy to represent Y acceleration. And the value that I came up with after some tweaking was 0.5 positive. So what this means is with every frame, we're going to alter the player's Y velocity, which is minus 4.5, by adding 0.5 to it. So the first frame, it'll be minus 4.5. The second frame, it'll be minus 4.0. The next frame will be minus 3.5. That doesn't line up right, but eventually the player's Y velocity will equal out to 0, which means they're going to stop right here. But we're going to keep adding that gravity, right? So the next frame, it'll be 0.5. So now, because the player has a positive velocity, they're going to be traveling in this direction, which is what we want. Right? We want it to go down this way. So the next frame will be 1. The next frame will be 1.5. So they'll start to accelerate faster and faster towards the ground, which again is pretty much how gravity works in the real world, more or less. So we will set this constant ddy value inside the player table. It doesn't have to be part of the player table. It can be just a constant defined somewhere, but whatever, we'll just put it here with everything else. Then every frame, when we update the dy, we're going to add our gravity, our ddy, to the player's velocity, the Y velocity. And we're also going to cap this so the player can only reach a max dy, because otherwise they'll just accelerate forever. Again, this is realistic, right? We do have the concept of terminal velocity in the real world. Eventually you'll stop accelerating due to gravity when you attain some speed. So there's precedent for this. And finally, we just update the player's Y position by the velocity until the player reaches the ground, that Y ground value there. So we know not to accelerate the player beyond the ground. That would also be weird. So now what we get when we do this, rather than flying into the air forever, is gravity eventually pulls us down, which is exactly what we want. And that looks and feels pretty good. We can see on both ramps, we get the result we would expect. Cool. One thing that kind of bothers me now is I feel like the player is still traveling a little too far in the X direction after they get off the ramp. It seems like a little bit too much distance for me, so I want to add some additional factor that kind of simulates the air resistance that they would experience while they were in the air. So because they're not on the ground, there's no friction with the ground, but there's still resistance in the form of air resistance. So I think if we account for that, it'll make the jumps feel a little bit more natural. This is actually fairly simple. What we'll do is when the player is in the air, I'll just kind of omit that part of the conditional for now, but when the player is in the air, we just multiply their dx by some constant factor. Here I've chosen 0.99. And what this means is every frame the player's dx is going to be 99% of it was the previous frame. So they'll kind of like gradually slow down, but not reach zero. It'll sort of approach zero. And again, this is a lot less severe than the friction with the ground, which makes sense, right? Air resistance, I think, is generally less severe than friction with like pavement or whatever. So this kind of feels realistic, and we can take a look at how it works in practice. When we go over this ramp, it's very subtle, but we'll slow down just a little bit more in the X direction than we did before. Whee! Whee! I think that about does it for the jumpy part and the gravity part, and we can finally move on to the cool part, the part with the angles. So when we go over the ramps, presumably right now the player is just like flat, which is lame. Like this, I mean, his board is like digging into the ramp. This is just awful. So what we want to do is take advantage of all these sweet angled sprites that we made way back when, and have the players' boards angle change depending on where they are on the ramp. So the entity that knows all about the angle of things is actually the ramps themselves. So you might remember earlier we added the second return parameter to when we look up the ranges that tells the rest of the game what the slope of each ramp is. We return the y coordinate of the ramp, but also what the slope we expect it to be, where negative numbers represent upward slopes, 0 is flat, and positive numbers represents downward slopes. The astute among you have probably already noticed that we have our sprites in a similar order, like this. So we're drawing this as the flat sprite, which would be 0, and if we go in the negative direction in the sprite sheet, we can see that we have upward sloping guy, and then if we go in the positive direction, we get downward sloping guy. So if our player sprite is at index 4, and we're drawing our player sprite like this, then we only need to add the angle of the ramp to that sprite index, and that will adjust our drawing function to get the correct sprite to display when the player is on the ramp. So let's have a look. So we've got 3 different slopes of ramp here, so we should be able to see all the combinations. So as the player approaches the ramp and the player's angle becomes -2, it's drawing the -2 sprite. So this looks a little bit better than it did before. Similarly, when we go over this ramp, we'll see it switches to the downward angle. And when we go up the really steep ramp, it'll use the really steep sprite. Same thing back down. And then for the little shallow ramps, there's a very subtle change in the sprite. Again, I need to get better at pixel art, but yeah, there we go. Oh, and it looks like a bug. He's kind of stuck in that position. I'll deal with that later. Now that we've got the player's sprite looking better when it goes over the ramps, we haven't actually given ourselves the ability to control the angle yet, so we can add that now. What we're doing is every frame that the right button on the D-pad is held down, we'll add a small number to the player angle up to some max angle, which is 3. If we do the same thing for the left direction, we'll just be subtracting a small amount from the player's angle up to a minimum of -3. Now, one other thing that we can do that I observed in the original game is to let the player give themselves a little bit of a boost when they're in the air. So when they hold the back direction, in this case left, when they're traveling over a ramp, this is gives them a little bit of extra elevation, but it also introduces some extra air resistance. So I've included that behavior here. I don't actually know why Excitebike has this. Maybe I'm not a good enough of a player to have ever had to use this, but it is something that I noticed. So maybe we'll find some way to use it like later when there's actual levels. All right, so just to make sure this works, we're going to go over the ramp, and that's going to give my player like an incline, an angle, and in midair, I'm going to hold down the right key to flatten the player out before he hits the ground. So let's try that. Here we go. There we go. Oh, I almost did it. I kind of screwed it up. Let me try again. I want it to be totally flat. Perfect. Okay, cool. And also, when I go over this ramp, if I hold left, he'll get a little bit of extra airtime. Might be hard to see, but trust me, it's happening. There we go. Okay, great. Same thing for these other ramps. We can kind of flatten this out. Also, I fixed the bug where the player's angle got stuck going over the shallow ramp, so progress. At the top of the video, I also mentioned there's that little mechanical quirk where your bike will actually bounce a little bit if you don't align it to the angle of the surface that you land on. So if you kind of go over a ramp and don't touch the D-pad, your bike will still be in an angle when you hit the ground, and you'll do a little hop or a little bounce. And that causes you to lose speed, and that's kind of like the whole mechanic that we want to emulate here. So I was trying to implement this, and I got stuck on it for a little while. So let me explain my first sort of non-working solution that introduced some additional problems for me, and then I'll explain how I solved it. So my first attempt looked something like this. I do a few checks for the player. So first I see if the player has a positive y velocity, a positive dy, because that means they're falling downward. The next thing I check to see is if they're near the ground, because just because they're falling downward doesn't necessarily mean we want them to bounce. So kind of near ground, I mean like basically on the ground, right? Like right there. And I also check to see if the player's angle doesn't match the ground angle. Now, if all those things are true, then what I do is I kind of want to flip the velocity, right? We want them to bounce. So we want to go from a positive dy to a negative dy. And so when I did this, I was like, yeah, cool, that'll work, right? Because it'll send them back up, and then gravity will pull them just like a little bit, like a really small dy. So they'll give them a little hop, and then gravity will just pull them right back down again. What ended up happening, though, the first time I did this was this. So let me go over the ramp, and we'll see what happens when the player hits the ground at the wrong angle. Oh, yeah. So one more time. For illustrative purposes is, yeah, the player is just like bouncing endlessly, which is not what we want. We want them to bounce once and then hit the ground. So what's actually going on here is if we go have a look at our conditional again. So what's happening here is our earlier conditional that's checking for the downward velocity and the player close to ground and the angle not matching, that's all triggering correctly. That part's working, but when the player returns from the initial hop, it triggers again because all of those conditions are true again. So they get upward velocity again, and they end up in the same loop, and that the result is this, somewhat amusing infinite hopping situation. I tried a couple of ad hoc ways to resolve this, but what I recognized is that I want to treat the condition of like the player is falling from a jump, like a proper going over the ramp jump, that state, and the player is falling from a hop, like differently, right? The player is in different states from our point of view, from our logic's point of view. So I wrote some quick state machine code to accommodate this. So what I mean when I say I wrote some state machine code is I tried to model the player in a series of states that each have their own logic to move from one state to another. So to give some examples, like the player normally is in this sort of like on ground state, which means they're just riding on the ground. And this actually includes ramps, right? Because the ramp is ground, it's slopey, but it's still the ground, right? So this is the first state, and the player has certain behavior when they're on the ground. Now, the other thing that can happen to a player when they're on the ground, they can't bounce just by being on the ground, right? So we know we can't move to a bouncy state, but we can jump, right? If we go over a ramp, we can move to the jump state. And let's say we want to have two jump states. Let's say we're going to jump upwards, right? So if they're moving in the upward direction, if they're moving in the upward direction, they can't bounce because they're not going to hit the ground moving upward, right? Unless we turn this into sort of a metal storm situation or we're inverting gravity. But no, that's not going to happen. From the jump up state, the only thing that can happen to them is they're going to move into the jump down state. Okay, now this is where things get a little bit interesting. Depending on the angle that the player hits the ground at, the state transition after jumping downward is going to be different. So if the player is aligned with the ground angle, then they're just going to go back to the on the ground state. They'll go like this. So if the player's angle matches the ground angle, they'll just go back to the ground state. However, if the player's angle does not match the ground angle, they're going to bounce. Okay, so if the angle does not match, they're going to bounce upward. And we'll have upward and downward bouncing states, just like we have upward and downward jumping states. It just makes it easier to isolate the logic. Now, from the bouncing up state, we know the only place the player can go, again, they're not going to hit the ground if they're moving upward. They can only go to the bounce downward state. Okay, and then from the bounce downward state, so the problem that we had up until now is the player was going from a downward bounce back to an upward bounce, back to a downward bounce. So we want to eliminate this part. So all we do now that we've isolated our logic, is we just don't allow the player to go from bounce down back to bounce up. We just make that impossible, right? The only thing that can happen to a player if they're bouncing downward, right, if they're traveling downward from the bounce, is that they go back to the on the ground state. And so that's what our player state machine looks like. So as long as we implement things this way, if we isolate our logic depending on the player state, we can prevent the weird bouncy bug that we just saw. So now, returning to our game with our state machine in place, what we would expect to see is the player goes over the ramp, we don't touch the angles, so they hit the ground with the wrong angle, and they do bounce, but they only bounce once, because once they've moved to the downward bouncing state, right, they're moving down after they've bounced, the only thing that can happen to them is that they go to the on the ground normal state again. So there will be no bouncing loop. So let's make sure that that works. I'm going to go ahead and send the player over the ramp, not adjust the angle, and one beautiful bounce. Let's watch that again. Oh, one beautiful bounce. All right. I think that might be what I title. If this becomes a series, I might title the series One Beautiful Bounce. So this is all thanks to the remarkable power of state machines. Really, if you find yourself in a position where the player's behavior is weird in certain situations, right? Like when he's doing one action and you expect him to do another action, you can maybe reevaluate how you're breaking up your states and just say like, okay, if the player's doing this, what possible actions can follow from what they're doing now, right? And that'll sort of maybe help you avoid the types of problems like we saw earlier with the hopping thing. I mean, it helped me avoid it. I shouldn't have tried to do that ad hoc. I should have just done the state machine to begin with. I forgot to display the code change. What the code actually changed to now is I created this player change state function that manages our state transitions. And I have these constants, like one defined for each state, like player state jump up, player state jump down, player state on ground, etc. So the conditional is the same. We only check this conditional in the code for the jumping down state, right? If the player is like coming downward from a jump. And if it matches, then we change them to the bouncing upward state. That gives them a little bit of extra upward movement. And critically to our game experience, we deduct some of the player's X velocity, right? That's the penalty for bouncing. If your angle does not match, you will actually lose a third of your DX here. You might be able to see this if you keep an eye on the DX when I go over the ramp. Air resistance will cause it to decrease a little bit, and then when he hits the ground, there'll be like a sudden deduction in the DX value. Check it out. So you might have seen it go from about 1.7 to about 1.1 in one shot, and that was the third of the DX being subtracted because of the bounce. Call it the bounce penalty. Bam, like that. So there we have it. I admit it ain't much to look at, but all the elements of a proto Excitebike are here, right? We've got decent feeling forward motion. We have a level format that allows us to include ramps and, change their sizes. We've got some sweet jumps, and we've implemented the angles and the bouncing mechanic, complete with a little bit of velocity penalty, that slowdown there from the original game. From here, I think this gives us a decent foundation upon which we could build a more complete game. But since this video is already super long and it's taken me forever to edit this, I'm going to wrap it up here. As for where I'm thinking of taking this, I'm actually not sure yet. Let's get our guy right at the top here. Oh, yeah. Yeah, I'm actually not sure. I may put this to the side for now and work on something else until I have something in mind that like I want to build on top of this. Similar to when I did Tree Fella, I kind of had like just the basic mechanics, and then I decided I wanted to add the crazy the overdrive mechanic. I don't really have an idea for this one yet like that, but I'll keep thinking about it. Anyway, if you're interested in checking out the code, you can find everything on GitHub. It's linked in the description. Feel free to clone it, to modify it, to use it in whichever way you see fit. You can do whatever you want with this code. It does not bother me. And hey, thank you for watching. It took me a while to get this video out the door because, while this prototype itself was pretty quick to put together, I was really challenging myself to do some more complicated editing techniques, and that took a while. Hopefully you noticed me, Senpai, and my cool editing techniques. So anyway, I appreciate your patience, and I appreciate all the time that you spent watching this video, and I hope whatever you're building, it is fun and rewarding. So until next time, I have been Eric, and this has been Radical Slice.